I'm just writing discussion topics, don't copy this
Are you
down.
color coding?
Yes.
I don't like color. Are you
Only
recording?
for like
Are you
1
recording?
or 2 lines.
Color coding's overrated. You're overrated. Whoa! Brandon, do you want one? Oh, do you want color coding's overrated? Do you want one? Do you want one?
Definitely not a top 10.
Okay.
Cole Bass, what do you top 10 wide receivers?
Before we start learning a super redundant, that's how I remember stuff. So I'm going to have to go way back. Just talk to somebody quickly about how aqueous solutions are made, positives, negatives, negative positives, dipoles, all that stuff. You should just be able to talk about it now. You probably don't need to draw it or think about it. Or, no, don't write this. Or look at anything. And then talk about precipitation reactions. That was like your warm-up. How do you know whether something's soluble? What are solubility rules that you've already memorized? And then tell somebody the 7 strong acids and the 8 strong bases. That you probably That you probably do need your notes for, because please don't say it wrong. Ready, set, go.
I know the 7 strong acids.
Today we're going to learn our final type of reactions. We did precipitation reactions, acid-base neutralization reactions, and the last one we're going to learn is redox reactions. Redox is going to be new to you. Remember the day, probably not, but remember the day you learned sig figs and you're like, wait, what? Like, what is the point of this? And you just learn like the rules of counting them. Today is going to be similar to that day at first. I'm going to give you a bunch of rules that for a long time are going to feel like arbitrary and meaningless, and they are until we do something with them. At the very end, it's going to kind of all tie together. So today's going to be kind of one of those days where you're like, wait, what? And then it'll come together. So let's talk about redox. Redox is a short way to say reduction oxidation or oxidation reduction. An oxidation reduction has to go together in a reaction. One cannot happen without the other one. Cold focus. So if we have, for example, copper solid. So think in your brain eyeballs. These are your brain eyeballs. Think in your brain eyeballs what copper solid looks like, okay? Like a penny, right? If we go from copper solid to a copper 2+ ion, that means it's an aqueous solution. It changes from copper color to a blue liquid color. All copper solutions are blue. Okay, so when the music starts, I want you to talk to somebody about how it goes from a neutral compound to a 2+. What happens with the electrons? Do they gain or lose them? Ready, set, go. In order to go from a 0 charge to a +2 charge, I'm going to have to lose some negatives.
Electrons.
And those are electrons. So to go from a neutral to a 2+, I would also be giving up 2 electrons. Okay? That becomes sort of like a product. Stop. It becomes sort of like a product. This is called oxidation. Oxidation is when the number goes up. It went from neutral 0 to +2. That's up. And they get that way by losing electrons. The electrons in the formula become like a product. They give them off. Okay? Now let's think backward the other way. What if I had a silver +1 ion? Ions are aqueous. The water molecules, oopsies. The water molecule surrounded and separated them. What would it take for that silver 1+ ion to become neutral again? What has to happen? Cole.
Does it have to lose 1 electron?
It has to add an electron. Electrons are negative. So in my brain eyeballs, I see these as number lines. Like mostly with math, I see things as number lines. It's super helpful. But if if I have a neutral here and I have a +1 here, I'd have to go back 1 to get to neutral, and the only way to go back is to add -1 to it. Okay? This is called reduction. Reduction means that the number goes down, just like the word reduce, by gaining electrons. Electrons are negative, they'd be taking us backward spaces. Okay? We are first going to learn how to figure out what the numbers are in order to tell if they are going up or down. You will have to identify things that are being oxidized, things that are being reduced based on those numbers. So I'm going to give you a bunch of rules. These rules are going to be meaningless at first, but we'll get there. So label this next one rules. These are rules for assigning oxidation states. The first rule is anything by itself has an oxidation state of 0. By itself means it is not in a compound. So by itself, these are going to be examples in brackets, is like if I just had an iron atom. This includes diatomics and things like diatomics. Compounds with itself. No other type of atom, no other element. It's automatically going to be 0. Rule 2. The oxidation state is the same as the charge or has to add to the charge. And I'll show you. So, Fe2 plus no longer has an oxidation state of 0. Now it has an oxidation state of 2 plus. It lost 2 electrons. But if we have like a polyatomic, like nitrate, all nitrates are soluble. That means when I add these oxidation states up of nitrogen and oxygen, it has to add to -1. Okay? Rule 3. Rule 3 says oxygen has an oxidation state of -2 except if it's a peroxide. And I'll show you what a peroxide is. So oxygen is always going to be -2. So like in water, H2O, not a peroxide. Oxygen is -2. A peroxide is when we have 2 subscripts of 2. H2O2, Na2O2, K2O2. It has to have the 2 2's. This is a peroxide. In this case, it's -1. In this case, it's -2. 100% the peroxide is going to be the question on the AP exam. 100% the peroxide is going to be on my quiz. 100% the peroxide is going to be on the test. It's the one, it's like a whole separate learning objective that you know that a peroxide has an oxidation state for oxygen of -1. Okay, I don't know. 4. Hydrogen is going to be a +1 if it's a cation. Cations are the positive ions. They are first in position. They're the first one in a compound. It's going to be +1. And the last rule is +1s are usually +1s. So this group 1 has a charge of +1. And usually it also has an oxidation state of +1. Like you can bet on it. The other one is -1s. These halogens in group 7 are usually -1. this point, you are basically just reading what you wrote. This is meaningless to you, but you need to read them to help you remember them. So read them to somebody, and then they read it back to you, and then we're going to do samples. Ready, go.
Okay. Equal by itself. By itself is 0.
Find number 11 in your sample house. I'm going to do a couple for you, and as I do them, I'm going to be thinking out loud. Granted, you are smarter than me most likely, so as I'm thinking out loud, and you're like, that is not how I would do it, then please do it your way. So I'm going to talk how my brain eyeballs see it and how I think about it, and go from there. Okay, so the first question asks us to find the oxidation number of sulfur. I'm going to find them for everything just to show you how I think. So I would look at H2S and say, okay, well, one of my rules is hydrogen is going to be +1 as long as it's in a cation position. Cations are positive ions. They're in the first position, so we're good. There are 2 of them. Each one has an oxidation state of +1. So the answer to the question is, what is the oxidation state of oxygen or of hydrogen? You would say +1. I know there's 2, but each one is +1, okay? So if this is +1, and one of my rules says it has to add up to the total charge, and my total charge is 0, then this sulfur must be -2. I have 2 +1s and a -2 adds to 0. Okay? Then for S8, one of my rules is that when it's by itself, no matter what it is, even if it's a crystal made with itself, the oxidation state is 0. So now look what's happening. Sulfur is -2 here, and it's 0 here. That's why sulfur doesn't really have a rule. It changes. Okay, now, with your battle buddies, see if you can work out SCl2. What are the oxidation states of sulfur and chlorine? What? Did you do it? Okay. What do you do if there's more than 2 elements? Let's do sodium sulfite. Okay, I'm going to start with my rules. The way I do things that have more than 1 element is I do the bread first, and then I do the turkey last. So I do the outsides and then do the insides. Oxygen is a rule. Oxygen is always -2, except if it's a peroxide. This is not a peroxide. Peroxides have 2s and 2s. Okay? So I know this is -2. Another rule says +1s are probably +1. So I'm going to go with that. My sodium is going to be a +1. Another rule I have is it has to add to its charge. Well, sodium sulfite does not have a charge, so I need to make it add up to 0. So I have -6 because I have 3 -2s. I have +1 times 2. So tell somebody next to you, what is this sulfur? Ready, set, go. 1, 2, 3, 4, 5, 6. -6 is 0.
So far, S has been a -2 to 0.
Yes. Now, with your battle buddy, do SO4 with this sulfate with a 2- charge. Make it add to -2. Ready? Go. Oxygen is always -2, except in a peroxide it's -1. This is not a peroxide, so it's -2. This is like shady here. Like, what am I supposed to do? I don't have rules for either of these. Default to it's going to be its charge. Okay, do the bread first, then the turkey. We already know sulfur is all over the board, so we're just going to assume this is going to be all over the board. So we already did this problem. Yup, this is a +6. Oxygen's always -2. I do not have rules to zinc, so I'm just going to default its charge. And this is still +6 because it has to add it to 2. Because its charge is 2. Sulfate is 2, so zinc is 2. Things by itself is 0. This is wrapping back to the beginning. Look what's happening to zinc. It starts at 0, and after the reaction, it's +2. We call that oxidation. The oxidation number went up. I like to do my number line like this, actually. From 0 to +2 is up. It got that way because it lost 2 electrons. Where did those 2 electrons go? It is not magic. They don't just disappear. Those 2 electrons went here. Copper went from a 2+ down to a 0. We call that reduction. This is a redox reaction because the zinc lost 2 electrons and gave them to the copper, who then turned from an aqueous to a solid. So that's how we changed phases from dissolved in water ions to full-on copper metal. Okay?
I did not, unfortunately.
All right, when the music starts, just tell the story of where the electron goes, and then I want to talk to you about your test model. Ready? Go.
So the electron goes across